You know that sinking feeling? You've just finished a CNC turning run.
Mm.
You're expecting this beautiful, smooth surface, and bam, wavy lines, chatter marks. They can drive you absolutely nuts.
Oh, absolutely frustrating.
Yeah.
And it's unfortunately a really common gremlin in CNC turning.
Mm.
Those visible patterns, they're a direct result of tiny vibrations happening right when the tool's cutting.
Exactly. And that's what we're really diving into today. Forget just, blaming the machine. We want to understand why it happens.
Yeah.
And more importantly, give you some actionable insights to maybe help banish those wavy lines for good. Think of this as maybe your shortcut to smoother finishes, less scrap.
Precisely.
Yeah.
Understanding the root causes, I mean, whether it's deep in the machine itself or maybe your tooling choices or even just how you've programmed the cut
Or wear and tear.
or, yeah, even the unseen condition of your equipment,
Yeah.
that's really the crucial first step towards finding a solution.
Right.
And this isn't just for, seasoned pros.
Right.
If you're involved in CNC turning at all, or frankly, even if you're just curious about precision manufacturing, there's definitely something valuable here for you.
And our discussion today, it comes from a pretty comprehensive look at all these interconnected factors that can feed into chatter in turning. Okay, so let's start unpacking this.
Let's do it.
We should probably begin with the foundation, right? The machine itself.
That's good.
Well, a less than solid machine is practically asking for vibration problems.
That's spot on. The overall rigidity and also what we call the damping capacity of your lathe,
Yeah.
they're absolutely fundamental. They can stop chatter before it even gets a chance to start.
Okay, so rigidity and damping.
Yeah. Think about it. If the whole machine structure can easily flex or vibrate when that cutting tool digs in, well, those vibrations are just going to amplify. They transfer straight to the workpiece.
Hmm.
And if the machine doesn't have good damping, it means it can't really absorb those vibrations effectively. So they just keep going, making things worse.
It makes me think of like trying to carve something intricate on a flimsy card table versus a really heavy solid workbench.
Exactly. Perfect analogy.
You can just picture which one gives you cleaner results.
Yeah.
So what actually makes a CNC lathe act like that wobbly table? What contributes to that lack of rigidity?
Well, a key concept here is something called system stiffness. And it's not just about the big iron casting of the machine frame,
Right.
It includes everything in that loop, from the concrete foundation the machine sits on, how well it's anchored, right through to how tightly you're clamping your workpiece and how rigidly the tool itself is being held. A solid foundation, proper anchoring, that's your first defense.
Okay.
But if any link in that chain is weak, lacks stiffness, say you're machining a long, skinny part without enough support,
Yeah, I can see that.
or maybe your cutting tool is sticking way out from the holder, too much overhang.
Yeah.
It's just going to deflect under the cutting pressure.
And that deflection, it isn't just like a one-time bend, is it? It's happening dynamically while the cutting's going on.
Precisely. That lack of stiffness leads to what we call reduced dynamic stiffness. And this really becomes noticeable, especially when you start pushing the cutting speeds up.
Right.
This can cause the forces between the tool and the material to kind of fluctuate rapidly,
Yeah.
bounce around, which in turn can trigger or really worsen vibrations. And this brings us to a fascinating idea: mechanical resonance.
Resonance. Okay, that sounds a bit like, when you pluck a guitar string and maybe another string starts vibrating too.
That's a perfect way to think about it.
Yeah.
Mechanical resonance in machining, it happens when the frequency of those forces generated by the cutting action gets really close to one of the machine's own natural vibration frequencies, or the workpiece's natural frequency. Think about pushing a kit on a swing. You push it just the right rhythm,
Yeah.
the swing goes higher and higher, right?
Yeah. Same idea. If the cutting forces happen to excite these natural frequencies, oh boy, the vibrations can amplify dramatically. That leads to really severe chatter. Improving the overall rigidity, the stiffness of the system, that helps push those natural frequencies higher, hopefully out of the range you're typically cutting in.
Okay, so a rock-solid stiff machine is absolutely vital, but you also mentioned damping. What's that doing exactly?
So damping, it's essentially the system's ability to soak up and dissipate that vibration energy. Turn it into heat, basically.
Oh, okay.
Because even on a super stiff machine, the act of cutting itself is still going to generate some vibrations, unavoidable.
Right.
If the system doesn't have good damping properties, those vibrations, they won't die down quickly. They'll just hang around, persist, and keep contributing to the chatter. The vibration energy isn't being absorbed effectively.
So practically then, how can you actually boost the damping in a setup? Are there things you can do? Yeah, there are a few effective techniques. Specialized tool holders, for instance, things like hydraulic expansion holders, they're designed specifically to absorb some of those vibrations using fluid pressure.
Interesting.
And for workpieces that are just inherently prone to vibrating, like thin-walled tubes or something.
Yeah, those can be tricky.
Definitely. A temporary fix, sometimes surprisingly effective, is to fill them with something, maybe wax or even fine sand. It adds mass and internal damping, helps quiet them down while you're machining.
That wax and sand trick. That's pretty clever, actually. Low tech, but effective.
Sometimes the simple solutions work.
Okay, so we've established the machine needs to be rigid, well damped. That's the foundation. But the tool itself, the thing actually doing the cutting that, seems like it would be another huge factor.
Oh, absolutely huge. Your tool choice, it's not just about grabbing something that fits. It has a really significant impact on whether you end up fighting chatter. I mean, the tool is the direct interface with the material.
Makes sense.
So its own properties, its shape, critically important.
So if we're picking a tool specifically trying to minimize chatter, what are the key things we should be looking at?
Okay, first off, think about the tool material itself.
Yeah.
Carbide is very common and often an excellent choice for turning tools.
Right, standard stuff.
Yeah, because it gives you that great combination of hardness and wear resistance. You need that to maintain a sharp cutting edge.
And a sharper edge means less force.
Generally, yes. A sharper edge usually means lower cutting forces and therefore less tendency to vibrate. Also, the physical size, the dimensions of the tool really matter.
How so?
A tool with a larger diameter, a bigger cross-section, and importantly, a shorter overhang. That's the distance it sticks out from the tool holder.
Ah, the overhang, yeah.
That's going to be significantly more rigid, less likely to vibrate. Think about holding a short, thick stick versus a long, thin one. Which one's easier to make wiggle?
The long, thin one, definitely. Makes perfect sense. Shorter, stouter tool, more stable.
Okay, what about those shiny coatings you see on tools? Are they just for looks? No, not at all. Those modern tool coatings, things like tin, Tycn, L203, they serve a very real functional purpose.
Like what?
They dramatically reduce friction between the cutting tool and the workpiece, and the chip. Lower friction means lower cutting forces and less heat generated right at the cut.
Ah.
And both of those things, lower force, lower heat, are really beneficial in minimizing vibration and preventing chatter.
So material, size, coatings are important, but the actual shape of the cutting edge, the geometry, that must also play a big role in how smoothly it cuts, right?
It's absolutely critical, yeah. Optimizing the tool geometry is key to controlling exactly how that cutting force interacts with the material being removed.
Okay.
Let's think about a few key angles. The rake angle, for example.
Uh-huh.
Generally speaking, a more positive rake angle lets the tool slice through the material more cleanly.
Like a sharper knife edge.
Exactly. Reduces cutting resistance,
Yep.
lowers the overall forces involved, which in turn minimizes that tendency for vibration.
Okay. What about the angle on the main cutting edge? It's sometimes called the lead angle.
Right, the major cutting edge angle or lead angle. You can adjust that to influence how the cutting forces are distributed. Sometimes a larger lead angle can help thin out the chip and direct the main cutting force more axially along the spindle axis.
Uh-huh.
And in certain situations, that can contribute to greater stability.
And the nose radius, that little rounded bit at the very tip, I know that affects finish.
It does, yeah. The nose radius is, well, it's a bit of a balancing act. A larger nose radius can definitely improve the surface finish, make it smoother, and it can add some strength to the tool tip too. But an excessively large nose radius can also increase the contact area between the tool and the workpiece. That can lead to higher cutting forces and, you guessed it, an increased risk of chatter.
So you're looking for the sweet spot again.
Exactly. You really need to find the right balance for your specific job.
Okay, got it. What about the clearance angle? I always thought that was just to stop the tool rubbing on the part it just cut.
Well, that is its main job, yes.
Yeah.
And preventing that rubbing is actually crucial for avoiding vibration too.
Ah, okay.
If the flank, the side of the tool below the cutting edge, rubs against the machine's surface, it generates friction, heat, and, well, more vibration. So yeah, sufficient clearance is vital.
Right.
And one more thing, chip breakers, we shouldn't overlook those.
The little grooves or features on the tool face?
Yeah. Well-designed chip breakers, they play a really key role in managing the flow of chips, curling them up and breaking them, getting them away from the cutting zone smoothly. That prevents them from interfering with the cut, which also contributes to smoother, chatter-free machining.
And I guess even the most perfect tool geometry won't help much if the tool's kind of loose in the holder, right?
Absolutely critical point. Ensuring that tool is clamped very tightly within a high-quality tool holder one that has good run-out accuracy. That's essential.
Run out accuracy.
Yeah, basically how precisely the tool rotates without any wobble or unwanted side-to-side movement. Any looseness, any significant run-out in that tool-holding system is practically an open invitation for chatter.
Okay, so rigid machine, rigid tool holding, sharp tool, right? Geometry. Seems fundamental. But what about how we actually tell the machine to cut? The speeds and feeds, the parameters.
Ah, yes, the cutting parameters.
Yeah.
Specifically, cutting speed, feed rate, and depth of cut.
Wait.
They have a really profound effect on vibration and chatter.
Right.
You can't just, pull numbers out of thin air or copy what works on a totally different material or setup. These need careful consideration for this specific job.
So let's start with cutting speed, the spindle RPM. How can that trigger chatter?
Okay, think back to those natural frequencies we talked about earlier, the resonance.
Yeah.
Sometimes just making a small adjustment to the spindle speed, maybe only 5 or 10% faster or slower, can be enough to shift the frequency of those cutting forces away from one of those resonant frequencies of the machine or the part.
Ah, just nudge it out of the danger zone.
Exactly. This seemingly small tweak can often make a surprisingly big difference in reducing chatter. But it's really important not to make wild, drastic speed changes without understanding why.
Why is that?
Because you might just stumble into another problematic resonant frequency. It's often like tuning an old radio. Small, careful adjustments are usually more effective than big knob spins.
So subtle tweaks, not huge leaps. What about the dangers of going, say, way too fast or way too slow with the speed?
Well, running at excessively high cutting speeds can generate a lot of heat, which isn't great for tool life, but it can also excite high-frequency vibrations, jittery kind of chatter.
Okay.
On the flip side, operating at very low cutting speeds, sometimes that can lead to a less stable cut. You might hear more of a low-frequency rumbling or heavy chatter. Not always, but it can happen.
Okay, so finding that optimal speed zone is key. Now, what about feed rate? How fast the tool moves along or into the part?
Right. Feed rate. The main goal here is to maintain a consistent chip load. That's the thickness of the material being removed by each cutting edge as it passes.
Chip load. Okay.
If your feed rate is too low, the tool might tend to sort of rub or burnish the material instead of cutting cleanly. That creates instability, friction, vibration.
Right, not actually cutting properly.
Exactly. But if the feed rate is too high, well, that increases the cutting forces, potentially overloading the tool, the holder, the machine. And that leads to increased vibration, too.
So another balancing act?
It is. And also, any inconsistencies in the feed rate during a cut, unless you've deliberately programmed a variable feed for some reason, can cause fluctuating cutting forces, which again can contribute to chatter.
Consistency seems to be the big takeaway there for feed rate. And finally, depth of cut. How much material we bite off in one pass. That feels like it would directly impact the forces quite a bit.
Oh, absolutely.
Yeah.
A large depth of cut generates substantial cutting forces. That significantly raises the risk of chatter, tool deflection, maybe even breaking the tool.
Makes sense. More material, more force.
Exactly. So often when you're trying to troubleshoot chatter, one of the very first adjustments to consider is simply reducing the depth of cut. Take a lighter pass. And for more challenging situations, it can be really beneficial to use tool paths that try to maintain a more constant engagement between the tool and the material. Avoid those sudden big changes in how much material the tool is cutting at once.
Smooth transitions.
Yeah. And if chatter is really persistent, you might just have to accept taking multiple shallower passes instead of trying to hog off all the material in one deep cut.
It really sounds like all these parameters, speed, feed, depth of cut, are totally interconnected. Changing one affects the others.
Precisely. You adjust one, you often need to tweak the others to keep things stable and efficient. It's a bit of an art as well as a science. Requires careful observation, listening to the cut, looking at the finish, and understanding your specific setup.
Okay, so we've covered the machine's rigidity and damping, the tooling material, geometry, holding, and the cutting parameters. That's a lot. But what if you've diligently checked all those things, you think you've got them dialed in, but you still have chatter? Could there be something else going on?
Yes, absolutely. That's a really important point. If you've addressed the rigidity, the damping, you're using good tooling, optimal parameters, and chatter still persists.
Yeah.
The problem might very well lie in an area that's often overlooked. Wear. Wear in critical machine components.
Yeah.
Particularly the spindle bearings and the guideways. This kind of wear It tends to develop gradually over the life of the machine, so it might not be immediately obvious.
Worn spindle bearings and guideways. Okay, that makes sense. Those parts definitely see a lot of action over time. How does wear in the spindle bearings specifically lead to chatter?
Right, so the spindle bearings, their job is to let the spindle spin smoothly, accurately, but also to rigidly resist all those cutting forces.
Okay.
Over time, especially with heavy use or lots of high-speed running, the internal parts of those bearings just wear down.
Hmm.
This wear leads to an increase in the internal clearance inside the bearing. We often call it play or maybe increased radial runout of the spindle.
So it gets a bit looser.
Exactly. When that happens, the spindle isn't held as rigidly as it was designed to be. It can deflect more easily when the cutting forces hit it. This results in a loss of that dynamic stiffness we talked about and reduced rotational stability.
Right.
And that instability creates the perfect environment for chatter to develop because the exact position of the tooltip relative to the workpiece becomes less consistent, less predictable from moment to moment.
So even a tiny bit of extra play in those bearings could show up as those wavy chatter marks on the final part.
Precisely. The cutting forces can easily excite and amplify even minute amounts of play in the spindle, leading to significant vibration right at the cutting edge.
Wow. Okay. And you also mentioned wear in the guideways. How does that cause problems?
So the guideways are those precision surfaces that, well, guide the movement of the machine's slides, like the carriage moving along the bed, the cross slide moving in and out.
Yeah, the ways.
Exactly. Wear on those surfaces, or on the mating surfaces of the slides that run on them, it diminishes the machine's overall precision and its structural rigidity. The slides might not move as smoothly, and they become less effective at resisting the cutting forces trying to push them around.
Okay.
And what's really interesting here is that wear, or even just poor lubrication on the guideways, can lead to a phenomena called stick slip.
Stick slip.
Yeah, it's where the slide momentarily hesitates, it sticks, and then suddenly moves or slips forward. Stick slips, stick slips. It's an erratic motion.
I can imagine that would cause vibration.
Absolutely. That jerky movement directly introduces vibration right at the tool. And much like with worn bearings, wear in the guideways also creates excessive clearance, extra space between the guideways and the slides.
More looseness.
More looseness, which means the slides aren't supported as rigidly as they should be. They can deflect or vibrate more easily under the dynamic loads of cutting. This is precisely why regular, thorough machine maintenance is so critical.
Like lubrication.
Proper lubrication of the guideways and spindle bearings,
Yeah.
and periodically checking for any excessive play and adjusting it if possible, like through the gibs on the slides. These things are absolutely essential for preventing chatter that comes from these often hidden sources.
So it really hammers home that it's not just about having the newest tools or the perfect program. Keeping the fundamental health and condition of the machine itself in check is absolutely critical for getting consistent, chatter-free results.
Precisely. You know, a machine that's been a reliable workhorse for years can gradually start showing chatter problems simply due to this inevitable wear and tear on those core mechanical parts. It's often a factor people overlook when troubleshooting. They jump straight to blaming the tool or the speeds.
Well, this has been a really, really enlightening deep dive. It's just so clear now that chatter and CNC turning, it isn't just some random gremlin appearing out of nowhere.
Not at all.
It's a direct result of vibrations, and those vibrations stem from this complex mix of factors we've talked about.
That's exactly right. Whether it's, not enough rigidity or damping in the machine structure itself, or maybe using less than ideal tools or geometry,
Or the wrong parameters.
or programming parameters that aren't quite right, or, as we just discussed, dealing with the effects of wear in those essential machine component spindle ways.
Yeah.
These are really the primary culprits behind those frustrating wavy lines.
And the encouraging part, I think, is that by really getting a handle on these causes, understanding them, and then addressing them systematically, you can actually make a tangible difference. You can improve the quality of your parts and hopefully reduce a lot of those production headaches.
Absolutely. It really boils down to taking a holistic view of the whole turning process, from the machine's foundation right up to the very tip of that cutting tool.
So maybe as you reflect on your own experiences with turning, think about which of these factors might be the one you've perhaps overlooked the most. Could a small tweak in cutting speed unlock a smoother finish? Or perhaps it's finally time to pay closer attention to those subtle signs of wear in your machine's spindle or guideways. What new questions has this whole discussion sparked for you about finally achieving that elusive, perfectly smooth, chatter-free finish? That's definitely something worth mulling over.